that's mod v. Right? Now, we want pumping to occur. Now, for pumping to occur, you need this double occurrence of the same symbol. Okay? So you like here, if you come down some path, in the same path, well, in the path, there will be two occurrences of R, and we proved that last time. Now, for that to happen, we want to find little p. That's like the smallest integer, positive integer you can have, so that all the strings greater or equal to it in length can be pumped. Now, think about what that means for a minute. So it means that to have pumping, you've got to have this vxy. You need that substring. So what's here, the u and the z, that doesn't get pumped, right? That just stays there. But you need this a double occurrence of some symbol, some variable, so that because the pumping is a consequence of having these two, what's the word? The double occurrence. The fact that you get a repetition. I guess that's the word. A repetition of the symbol. It gets used twice, at least, right? As you come down the path. All right. So we want this substring here, vxy. We want that the size of it to be less or equal to p. We want p to be large enough that it includes this substring vxy. Now, what's the smallest vxy that we could get? Well, if we make if this second r here is just one here, I've got to put it one here. It's just one step away from its leaf. Okay, and the number of steps between the first occurrence of R and the second occurrence of R, the variable, the second time that same variable appears, the minimum number of steps between here and here, minimum number, has to be mod v plus 1. Now, can you see why that is? Because what is mod v? It's the number of different variables in your set of variables in your grammar. Okay. So if the number of steps from here to here, number of derivations, number of times you apply a substitution rule, if that distance from here to here were just mod v, it's possible. This is improbable, but it's possible. You might get each symbol used just once, and hence no repetition. But if the number of steps from here to here is mod v plus 1, there has to be a repetition. Okay, so the minimum number of steps between here and here for this to be r and r is mod v plus 1. Okay, now okay, so that here's a variable. That's a variable. It's not a terminal. It's a variable, right? Now the minimum number of steps from here to your terminal, well, it's just one, right? You just go from a variable to a terminal, so it's just one. So from here to here, the minimum number of steps will be this plus 1, right? So you're going from here to here. They're all variables. You're all the way through this path from R to R. They'll all be variables, and then the very last one from the second R to its leaf, a terminal variable. That's just one step. So here you'll have, from here to here, you have mod v plus 2 steps, minimum. Okay, minimum. All right. Now, what's the largest string you can generate in mod v plus 2 steps? Think about that. And so we've got to choose. We have to choose a p that's larger than that. Okay? If we chose it smaller than that, we've got problems. Okay, so from the first R here, what's the biggest, the longest string we could generate in theory from that R? Well, remember we talked about little b. Little b, if you remember, was you look at all your rules in your rule set, and you look at the right hand side of each rule, and you find the number of symbols in the right hand side, and then find what's the largest number of symbols on a right hand side. So you look at each rule, and at each rule you write down the number of symbols it has on its right hand side, and you look at all those numbers and find the largest one and call that little b. Right? Okay, so starting here and in mod v plus 2 steps, what's the largest string you could generate here? Well, it would be b to power this much. Can you see that? Like, if here's a node here, let's say, and then say you apply the right hand side. You apply the rule that has b symbols on its right hand side. Well, then you'll get like little b children, right? From that parent node, you'll have like little b, and in theory you could have those expanding. So in 2 steps, the length of your string, your what's the word? Intermediate string, could now be b squared, right? Each one here goes b ways. So you have b times b, so b squared. And if you go down mod v plus 2 steps, the maximum, the maximum length of this string could be little b to power mod v plus 2, right? So choose your little p, your pumping length, to be greater or equal to that. Yeah, well, let little be equal to that. So you let your pumping length be equal to that. Now, now you could have x. No, what was it? U. You could have u and z be 0. I guess that's possible. There's nothing in pumping lemma restricting that. So you need. So the maximum length here would be this, right? That's the maximum possible. So in practice, the length of this, the length of vxy, mod vxy, is going to be less or equal to this, right? That's critical, what I've just said, right? Okay, so if we let p be equal to that, therefore the length of this is less or equal to this, which is p. And there it is. There's our third condition. Okay? So let this be a kind of object lesson to you. This is the kind of thing that Sipser is assuming of his students. Now, if I were one of his students, well, probably not, because those guys are really smart, the MIT students. Like I said, minimum IQ of about 160. 160. I mean, the average theoretical physics professor in America has an IQ of 170. Right? So these students, undergrads, are really smart. Okay. All right. So Sipser takeaway message, Sipser assumes, I think more unconsciously than anything, that his student audience are capable of filling in the lines sort of like this, as I've done. I think he's been a bit sloppy with his editing. He gave two different values for P. That's not acceptable. So if ever this video gets back to him, if ever some MIT student is watching this and goes to Sipser and says, who knows if, when this may happen. But, well, MIT professors, I suppose, are very busy. They don't spend too much time editing the fine details. Errors like this slip through. But still, it is sloppy editing. Okay, now let's start on the first of three applications of the pumping lemma devised for context-free languages. And we've been through this kind of thing 5 times already, so you'll be fairly familiar with it. The procedure is much the same. So we do it by proof by contradiction. Usually, we're given a language. Example 2.36. We just started doing this previous session. So here's your language. Call it B. Its strings are of the form A to the n, B to the n, C to the n, where n is an integer non-negative, so greater or equal to 0. And I guess the alphabet, well, the set of terminals, capital sigma if you like, the alphabet is just A, B and C. Okay? And you're asked to prove that that language B is not context-free. It is not a context-free language. Right? And you'll use the pumping lemma for context-free languages. You'll use that version, this second version of the pumping lemma to prove that that's the case. And the style of the proof, as usual, done it already 5 times. We'll do it another 3 more times. The style of proof will be proof by contradiction. Okay. So in other words, assume the opposite and derive a contradiction. Therefore, what you assumed is false. Okay? The classic proof by contradiction. We'll talk about this at length. Okay. All right. So assume the opposite. In other words, assume that B is a context-free language. Okay, and we'll derive a contradiction. Now, the heart of the proof each time, you probably know this already. The art, I suppose, the most difficult part, well, debatable, is